I want you to picture something for me. You're just casually scrolling through your feed and you see a photo.
Okay.
It's a cat. But not just any cat. This cat is wearing these perfectly round reflective sunglasses. Now, if I ask you to just describe that image, what do you say?
I mean, pretty standard stuff. I'd say a fluffy gray cat wearing sunglasses. It's basic object recognition. I see a cat, I see glasses, I list them.
Right. It's simple. But what if I showed you a photo of this stunning purple sunset over the ocean? The waves are crashing, the sky is just on fire. And I said, don't just describe it. Write me a romantic message that fits the mood of this photo.
Ah, yeah, that's a significantly heavier lift. You're asking for tone, for emotional resonance.
Cultural context, even.
Exactly. You aren't just identifying pixels anymore. You have to understand what a sunset actually means to a human being.
Which is hard. And that gap between seeing a, red circle and understanding romance, that is the leap we are diving into today.
It's a massive leap.
It is. We are looking at a paper from Salesforce Research titled BLIP-2, Bootstrapping Language Image Pre-Training with Frozen Image Encoders and Large Language Models.
Which I know is an absolute mouthful of a title, but it really marks a pivotal moment in generative AI.
So our mission for this deep dive is pretty specific. We want to figure out how to get artificial intelligence to bridge that exact gap between seeing the vision part and speaking the language part.
Right.
But here's the catch for today's topic. We want to understand how they did it without needing a supercomputer the size of a city block.
Because that's the real key here, efficiency.
It's basically a David versus Goliath story. You've got this new model, BLIP, stepping into the ring against these absolute industry giants like DeepMind's Flamingo model, and somehow it holds its own.
It actually wins.
Right, it wins, and with a fraction of the resources.
A tiny fraction. But before we get to the whole victory lap, we should probably deal with the obstacle course. Why is teaching a computer to see and speak so insanely expensive in the first place?
Let's break that down. So, my understanding of the current state of vision language pre-training VLP, for those taking notes, is that it usually involves this thing called end-to-end training. Paint a picture of what that actually looks like in a data center.
Okay, imagine you have a massive neural network designed to understand images. That's your vision tower.
Got it.
And then you have another massive network designed to understand text, your language tower. In end-to-end training, you are effectively trying to wire those two behemoths together and train the whole thing at once.
Which sounds heavy.
It is. You're updating billions of parameters across both models simultaneously, and you're doing it using billions of image-text pairs.
So every single time you want to teach the model a new trick, you basically have to fire up the entire factory.
Essentially, yes. And as these models get larger, which, they always do, the computational cost doesn't just go up linearly, it skyrockets. It becomes completely prohibitive for anyone outside of a few massive tech giants.
Okay, so that's the cost problem, but there's also a compatibility problem, right? The paper talks about a modality gap.
Right, the modality gap.
Right.
Think about the tools we already have just sitting on the shelf. We have these incredible large language models, LLMs like OPT or FLAN-T5.
The text geniuses.
Exactly. They've read the entire internet. They are absolute geniuses at text. But they are entirely blind. They have literally never seen an image in their training.
And on the other shelf?
On the other shelf, we have image encoders, things like the vision transformer from CLIP. Now, they are excellent at processing pixels and finding patterns in visual data.
But they don't speak English.
They don't. They are unimodal experts, single mode only.
So you basically have a blind poet and a mute photographer, and you need them to collaborate on a complex project.
That's a really fantastic way to put it, actually.
So the obvious solution seems to be, well, just force them to learn each other's skills. Take the LLM and just start showing it pictures until it gets it.
You can try that. People have.
Yeah.
But you run into a massive risk. It's called catastrophic forgetting.
Which sounds like a terrifying medical condition, but I assume it's bad for code.
It's devastating for code. Imagine you spent years becoming absolutely fluent in French.
Okay.
Then someone forces you to intensely study quantum physics for a month straight.
Yeah.
But in the process of rewriting your brain to understand the physics, you accidentally overwrite the part that knows French grammar.
Oh, wow.
Yeah, so you come out the other side knowing physics, but you literally can't speak anymore.
And that's catastrophic forgetting.
Yes. If you start tinkering with a pre-trained LLM's weights to teach it vision, it starts losing the language abilities that made it so useful in the first place. You damage the original genius.
So Salesforce Research looks at this problem and says, okay, we aren't going to retrain the genius. They propose this idea of bootstrapping.
Exactly. Bootstrapping in this context means utilizing the powerful resources you already have without altering them at all.
Freezing them.
Right. BLIP-2 keeps the image encoder frozen. The weights do not change. And it keeps the huge language model frozen too. Its weights don't change either.
Okay, but if the photographer is locked in a glass box and the poet is locked in a soundproof room, how do they communicate? You can't just tape them together.
No, you need a translator. Or, more accurately, a bridge. And that is the core innovation of this entire paper. They built a lightweight module called the Querying Transformer, or Q-former for short.
The Q-former, it kind of sounds like something out of a Marvel movie.
It is the hero of this story, definitely. But it's surprisingly small. We're talking about just 188 million parameters.
Which is nothing these days.
In the world of modern AI, where we casually deal with hundreds of billions of parameters, 188 million is tiny. It's incredibly lightweight.
The paper describes this Q-former as an information bottleneck. Now, usually when I hear bottleneck, I think of traffic jams or a slow Wi-Fi connection. Why is a bottleneck a good thing here?
Well, think about the difference between raw data and actual meaning. An image contains millions of pixels, the exact color of every single blade of grass, the subtle shadow on a rock.
Right. Way too much detail.
If you shove all that raw pixel data directly into a language model, you're just going to overwhelm it. It's too much noise.
It's like trying to drink from a fire hose.
Exactly. So the Q-former acts as an intelligent bottleneck. It intentionally filters out all that visual noise and extracts only the most useful features.
The semantic concepts.
Right. The concepts that the LLM actually needs to generate text. It's not just passing data through blindly. It's curating it.
So it's kind of like a translator at the UN. The speaker might go on for 10 minutes in their native language, detailing every historical nuance, but the translator just sums it up for the earpiece like, the delegate is unhappy with the trade agreement.
That is the perfect analogy. The Q-former translates raw vision into pure language concepts.
Okay, I'm sold on the concept, but I want to get into the gears of this thing. How does this little 188 million parameter module actually learn to do that translation if the other two giant models are totally frozen?
Right, the training. The paper breaks it down into two very distinct stages.
And this two-stage process is critical, right? Stage one is called vision language representation learning.
Which is really just a fancy way of saying teaching the Q-former how to see.
Okay, so at this stage, the LLM isn't even in the room yet.
Not at all. It's just the frozen image encoder and the Q-former. The Q-former connects to the image encoder using a set of learnable queries.
Learnable queries. I actually struggle with this part of the paper a bit. Are these like literal questions? Like it asks, is there a cat in this picture?
Not in English, no. Think of them as vectors. They're mathematical slots that are just hungry for information.
Okay.
Imagine you have 32 empty slots.
Okay, 32 slots.
The Q-former casts these slots into the image encoder almost like fishing lines. Each line learns to hook onto a different type of visual information. One query might learn to look for shapes, another looks for textures, another looks for spatial relationships between objects.
So they're learning how to extract the right information.
Yes. And to make absolutely sure they are extracting the right information, BLIP-2 forces the Q-former to run through three specific drills, three learning objectives.
It puts it through boot camp.
Basically. The first is image-text contrastive learning. It looks at a massive batch of images and text and asks which of these go together. It's aligning the visual representation directly with the text representation.
Like matching the picture of the actual cat to the word cat.
Exactly. The second drill is image-grounded text generation. Here, the Q-former actually tries to generate the caption itself. It practices describing what it sees.
Got it. And the third?
The third is image-text matching. This is a hard binary check. It looks at an image and a piece of text and has to say true or false. Do these actually match? This forces the model to pay extremely close attention to fine-grained details.
Now, before we move to stage two, I want to touch on the data itself. Because you can have the most elegant architecture in the world, but if you train it on jank, you just get junk out.
Oh, absolutely.
The paper mentions they used 129 million images.
It's a massive scale. They pulled from COCO, Visual Genome, Land 400M.
But they didn't just dump all that data straight in, right? I noticed a section on something called capfilt. That seemed really important.
It's crucial. Look, a lot of images scraped from the web have terrible alt text. A beautiful photo of a dog might just be captioned DSC0045.jpg or simply cute.
Which is useless for training. Garbage in, garbage out.
Right. So they used a method called caption filtering, or capfilt. They actually took another AI model and generated brand new synthetic captions for all those web images.
Oh, wow.
Then They used a filtering model to look at both the original human caption and the new synthetic one, and it just threw away whichever one was worse.
That is wild. They used AI to clean up the mess that humans made of the internet just so the next AI could learn better.
It's becoming a huge recurring theme in modern AI research. Synthetic data is a primary quality control mechanism now.
Okay, so let's recap where we are for everyone. Stage 1 is done. The Q-former has survived boot camp. It knows exactly how to fish relevant information out of an image. But we still haven't produced that romantic poem about the sunset. The Q-former understands the image, but it's not a poet.
Which brings us to stage 2, vision-to-language generative learning. Now, we finally bring in the frozen LLM. We bring in the poet.
This is where we actually hook the bridge up to the final destination.
Exactly. We attach the Q-former to the LLM. But remember, they still speak fundamentally different languages. The Q-former outputs these visual features it collected, but the LLM only expects text.
So how do you trick the text model into processing visual info?
You use a fully connected layer to project the Q-former's output directly into the LLM's input space. Effectively, these visual queries become soft visual prompts.
Soft prompts, that's another term that feels a bit slippery.
Think of it like this. A hard prompt is actual text you type on your keyboard, like write a story. A soft prompt is a vector. It's a string of numbers that hits the LLM's brain in the exact same place that the text write a story would hit. But instead, it contains the pure essence of the image.
So it's almost like telepathy. The Q-former isn't literally saying the English words sunset and purple. It's beaming the mathematical concept of a purple sunset directly into the LLM's cognitive stream.
That is a very poetic way to put it, but it's highly accurate. It basically whispers the visual context to the LLM. And because the LLM is frozen, it just reacts to this mathematical input the exact same way it reacts to text. It just starts generating words based on that soft prompt.
And this modularity is exactly why they could experiment with different brains, right? The paper mentions they tried this setup with both OPT and FLAN-T5.
Yes, OPT is a decoder-only model, very similar to GPT-3. It's fantastic at just continuing a sentence naturally. FLAN-T5 is an encoder-decoder model. It works more like a translator. It's much better at following strict instructions.
And the cool part to me is because the Q-former is the only thing bridging them, if a much better LLM comes out next week, you don't have to retrain your entire vision system from scratch.
Precisely. You just swap out the LLM, retrain just that tiny lightweight Q-former to align with the new brain, and suddenly your vision system is 100 times smarter. You've completely future-proofed your architecture.
So does it actually work, or is this just a really elegant architectural diagram that looks good in a PDF? Because the examples they provided in the paper, I mean, some of them are genuinely funny.
It works remarkably well, and they specifically test it on zero-shot tasks.
Meaning the model has never seen these specific photos or these specific questions before. It's totally improvising.
Right. So going back to your intro, they showed the model that purple sunset and gave the prompt, write a romantic message that goes along with this photo.
And instead of just saying red sky, water, clouds, it wrote, love is like a sunset. It's hard to see it coming, but when it does, it's so beautiful.
That requires mapping the visual of a sunset to the abstract human concept of love and beauty. It's real creativity.
But my absolute favorite example from the paper was the house. They showed it a photo of a house that was built entirely upside down, roof on the grass, foundation up in the air.
Right, like the WonderWorks buildings.
Yeah. And they asked, is this photo unusual? The model said, yes, it's a house that looks like it's upside down. But then they pushed it. They asked, how could someone get out of the house?
This is the reasoning test. This is where it gets interesting.
And the model answers, it has a slide on the side of the house.
Think about what had to happen computationally there. First, it had to identify a slide, which is a really small detail on the side of the building. Second, it had to actually understand the physics of the situation. It had to reason, the door's on the ceiling, I can't walk out. A slide is a valid exit strategy.
That is visual knowledge reasoning. It's not just labeling objects anymore. It's actual problem solving based on visual evidence.
And then there's the pop culture knowledge. The Titanic example.
Oh, right. They show it a single frame from the movie Titanic. Jack and Rose at the bow of the ship. No text anywhere, just the image. The prompt is, what happened at the end of this movie?
And BLIP-2 just says, the Titanic sank.
Which is true, but then they push it again. Did Leonardo DiCaprio's character survive?
And it replies, no, he drowned.
That's amazing because drowning isn't anywhere in the picture. The picture is literally just them standing on a boat. The model recognized the specific movie scene, accessed the LLM's internal encyclopedia about Titanic, retrieved the plot summary, and answered the question.
It's synthesized visual recognition with external world knowledge. That is the language-image bridge in full action.
So it's incredibly smart. But let's go back to the David versus Goliath aspect. How efficient is this really when put to the test?
Well, they compared BLIP-2 directly to Flamingo 80B, which is DeepMind's massive, state-of-the-art vision language model. On the standard benchmark for answering questions about images, it's called VQAV2, BLIP-2 scored 8.7% higher.
That's a very solid win. But what about the size comparison?
BLIP-2 achieved that higher score with 54 times fewer trainable parameters.
54 times fewer. That is staggering.
It is. Instead of needing a massive warehouse full of GPUs just to train the model, you could potentially train this on a standard, robust university cluster. It completely changes the economics of who gets to do this kind of research.
It democratizes it. You don't need Google money to build a Google-level model if you use this bootstrapping technique.
Exactly.
However, we do have to keep it real for everyone listening. It's not perfect. The paper shows some failure cases that are frankly hilarious, but also kind of concerning if you trust the AI too much.
Yes. The hallucination.
The Einstein one killed me. They show a photo of Albert Einstein, and they ask, what is a famous quote by this person?
And BLIP-2 very confidently replies,
Yeah.
"The world is a book, and those who do not travel read only one page."
Which is a lovely quote.
It is lovely, but it was written by St. Augustine, not Albert Einstein.
So what went wrong there? Did the vision part fail?
No, the vision part worked perfectly. The prompt Einstein successfully made it to the LLM. But LLMs are probabilistic. It associated Einstein with the concept of smart, profound quotes, and it just grabbed the wrong one. It's a knowledge retrieval failure, not a vision failure.
Right, it's that confident bluffing we all know and love from text chatbots just carried over.
Exactly. And there's another limitation tied directly to the frozen aspect of this whole architecture. Since you aren't updating the LLM, you are stuck with its knowledge cutoff date. They showed the model a picture of an iPhone 14. Visually, the model saw the new camera bump, the screen, everything. But the text output called it an iPhone 11.
Because the LLM hasn't read the news in 3 years.
The eyes are young, but the brain is old.
That's a really great way to conceptualize the risk here. Even if your camera is shooting an 8K resolution, if the brain processing the image is running on 2020 data, you're going to get the wrong answer.
There is also a technical limitation regarding in-context learning. BLIP-2 struggles if you try to teach it a pattern mid-conversation.
Like showing it a sequence. Dog leads to woof, cat leads to meow, and then showing a picture of a cow and expecting it to say moo.
Exactly, it fails at that. The authors think it's because the training data was just single pairs. One image, one caption. It literally never learned the concept of a sequence of examples.
So it basically has zero short-term memory for patterns.
Not yet, anyway. That's likely the next step for researchers creating data sets with interleaved images and text conversations to teach it that specific skill.
So pulling this all together, what is the big takeaway for someone listening to this right now who isn't an AI researcher? Why does BLIP-2 actually matter to them?
The big so what is that we have found a way to recycle intelligence. We don't need to burn a forest of energy to train every single new model from scratch. We can take the best vision systems, the best language systems, and just build a really smart, lightweight connector, the Q-former, to bridge them.
It's modular AI, like snapping Legos together.
It dramatically accelerates innovation. It means we're going to see smarter assistants, better search engines, and tools that can truly understand the visual world, accessible to way more developers.
I keep thinking about that final image in the paper's examples, the one with the man and the chicken.
Oh, yeah. A classic weird internet photo, a man screaming, running away from a chicken on a farm.
The prompt asks, what does the man feel and why? And BLIP-2 says, he is scared of the chicken because it is flying at him.
It correctly identified the emotion, fear, and the direct cause, the chicken's action.
That's the real aha moment for me in all this. We are moving past AI that just lists objects like a toddler. Man, chicken, grass. We are entering an era of AI that understands narrative. It understands why the man is running.
It's true visual knowledge reasoning.
And if this is what we can do with a frozen, slightly outdated LLM and a tiny 188 million parameter bridge, imagine what happens when we plug in the next generation of brains.
It's going to see complex relationships in our photos that we might not even notice ourselves.
Absolutely. But let me leave you with this one final thought to mull over. If we can bridge vision and language this cheaply and this efficiently, what happens when we move past static photos? Imagine this lightweight bridging tech applied to the real-time video feed of your augmented reality glasses. You wouldn't just have a chatbot in your pocket anymore. You'd have an AI co-pilot literally watching the world with you, instantly whispering contextual realities into your ear as life happens.
That is a fascinating and maybe slightly overwhelming future to think about.
It is both exciting and a little bit terrifying. Thanks for taking this deep dive with us today.
Always a pleasure.